Okay, so now we're going to talk about another kind of test, which is going to be the Chow test. And we can use the Chow test to test if different groups follow the same kind of regression function. To test null hypothesis. That groups or populations follow the same regression function, versus alternative, that one or more slopes differ, that one or more slopes differ across groups. And so let's, again, like usual in this class, let's make it pretty general. Like, let's say in general, let's start with two groups. Let's call them, we can have G equals 0 or 1. So there are two different groups. And let's say we want to test if intercepts and slopes are the same across both groups. Oops, no E there, across both groups. So let's just have a Y for our independent variable. And so Y, we have this beta G 0. So this is the beta 0 for group G, and G could be 0 or 1. So each group could have their own intercept. Same with this first slope parameter. There could be 0, 1, which is the slope parameter, this first one, let's put x1 here. So this is beta 1 can be different values for when group equals 0 or 1. So the slopes of these two different groups could differ. And we could do that for all these different groups. Beta g k, I guess it would be xk plus u. So for g equals 0 or 1. I mean, we could have 3 groups, 4 groups, 5 groups, the same thing. All there is kind of more and more parameters in these models, right? So let's erase this and talk about this test. So let's write out that model again. So we had y equals beta g0 plus beta g1 times x1 plus all these other ones, and then beta gk xk plus u. And remember that our hypothesis here that each group has the same intercept and slopes. So if this is our hypothesis, we have to think about how many restrictions we're placing, right? And so we have k independent variables plus 1 intercept. And so essentially we're saying for one group, their k plus 1 parameters are equal to the other group's parameters. So this involves k plus 1 restrictions. So we're making k plus 1 restrictions for the hypothesis test, where we're testing whether all these parameters of one group are equal to the other. Now, if instead we're allowing the intercept to differ, but just had the same slope parameters, if that was the test we were doing, there'd only be k amount of restrictions. And also keep in mind the unrestricted model the degrees of freedom for that model is going to be n, so that's the total like maybe n0 plus n1, so group 0 and group 1, so the number of observations in each of the groups added up. Let's say that's what we're denoting n here. N0 is a number of observations in group 0, N1 is a number of observations in group 1. Then the degrees of freedom are going to be n minus, and now we have to think about all the parameters that we'd be estimating in the model. Well, we would have k plus 1 parameters for group 0 and k plus 1 parameters for group 1. So here it's n minus 2 times k plus 1. That's the number of degrees of freedom in the unrestricted model. So, we can start to think about expanding the number of groups and how that might affect the degrees of freedom and the number of restrictions. So just think about what happens if there's 3 groups. How do these two things change? All right, so we would know if this was just a regular test, we know we need to do an f-test, and we know what the f-test looks like. You could do the SSR version. It's the SSR of the restricted minus the SSR of the unrestricted, Q is the number of restrictions. That's the number of restrictions we just figured out, but this is just the regular formula we're used to. This is the SSR unrestricted. And we normally have n minus k minus 1 here, right? So this is the kind of the normal formula that we deal with. So what it looks like now with this Chow test, we're going to kind of transform it. And the key is we can get the unrestricted model. We can get the SSRU by running separate regressions on each group. So we'd run, if we call this 1, on just people in group 0. We could call that SSR 0. We could run the same regression just on people in group 1. So in the other group. So I don't have a circle around it, just 1. Call that SSR 1. This is supposed to be 0 there. And then we can think about what our F-stat looks like. We're calling it a Chow test, but essentially it's like a special case of an F-test. Just to deal with, that just can use this this kind of key fact to help us maybe simplify what regressions we have to run. And so now the F-test, or the Chow test, let's just write Chow, is going to be to the SSR restricted. So that means that everyone has the same intercept and slope. So essentially to get this, we're going to run 1 on everybody. So both group 1 and 0. So to get the sum squared, that's the restricted one. So we're making them all have the same intercept and slope. So we just run that regression with everyone in our sample, both group 1 and group 0, to get the SSRR. And the key here is that we can just add these two SSRs together by running this regression separately on the groups. If we run them separately, that allows them to have the same different intercepts and different slopes, just because we're running them separately. There's no constraints. So instead of SSRU here, we have SSR 0 plus SSR 1. The number of restrictions is k plus 1. The SSRU again is SSR 0 plus SSR 1. And then we're dividing by degrees of freedom. Well, we figured out the degrees of freedom, n minus 2 times k plus 1. So this is our Chow test. So it's just like an F-test, but it's testing whether kind of the slopes and then sometimes the intercepts are the same across groups or differ. And it just allows us to use this special case where we can run the regression separately on the groups to get the unrestricted regression, which is allowing the slopes and the intercept to be different across these groups. And again, so think about what happens if we had 3 groups. Well, we'd have an SSR2 there, an SSR2 there, and then think about what happens to the number of restrictions. Well, then we'd have 2 times k plus 1 restrictions. Or we'd have n minus 3 times k plus 1 would be our degrees of freedom. Start thinking about that because it's come across sometimes on past exams.